Okay, so today we're looking at 14B. It looks at counting ordered selections, and we're going to also have a look at permutations. So we need to start thinking a little bit differently when we're looking at this topic, because it's different to anything that we've done before. So I'm going to read what's in the box there. It says if one event can happen in A different ways, and I'll just highlight that, and a second event can happen in B different ways, and a third event can happen in C different ways, and so on, then successive events can happen in A, B, C different ways. Now, what I want to get us to do with these questions is we want to have a think of each different event or each thing that happens individually. So the first example here is it looks at the car number plates, and you probably can figure this one out anyway, but this is looking at the maths behind what's happening. So a car number plate in New South Wales has 3 letters followed by 2 numbers. So I'm going to box it up like this because I'm going to give everything a particular spot. So we've got 3 letters and 2 numbers. So we've got letter, 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 number, number, number. Oh, sorry, it has 2 numbers, not 3 numbers. Sorry. There we go. So 3 letters and 2 numbers and a letter at the end as well. Like that. Okay. And how many number plates are actually possible? So we want to have a think about that. So how many letters have we got in the alphabet? We've got 26 letters. And how many numbers have we got? Well, we can have numbers from 0 through to 9. So we've got 10 different numbers. And what we're assuming here is that we can get repeats of letters and we can get repeats of numbers. So we've got 26 possibilities that we could have for the first letter. And in our number plates here, we can have double up, so we can still have 26 variations for our second letter and 26 for our third letter. We could have 10 variations for our number and 10 variations for the next number, and we've got a letter tacked on the end, which is still 26 combinations. So what we want to do is times each of these together, and that's going to get our actual possible number of number plates that are possible. So just pop that in your calculator. If you pop that in, you're only going to end up with 45,697,600 possible number plates. And that's allowing for repetition in there. But let's have a think, and this is not part of this question, but we need to start thinking this way. What would happen if we didn't have repetition? So that one says we can have repetition, we can repeat the numbers. If we have no repetition, let's think about what's going to happen there. I'll just box this up again. I like to box it up so we have an actual place for each of our numbers. Okay, so we can still have 26 letters for our first one. There's 26 possibilities. What we're going to assume is that we've used up one of those letters here. So maybe it's A. A's been banked away, so we can't use that again if there's no repetition. So we'd only have 25 to choose from for the second letter. We'll assume that another letter's been used. Maybe it's B. We don't know what it is. There's only 24 letters to choose from for the next position for the letter. And likewise for the last one, if we've used 3, then we're only going to have 23 possibilities for that last one, assuming there's no repetition. So number-wise, we've got 10 numbers to choose from. If we can't repeat our numbers, then we would have 9. So if we're multiplying all those together, we're basically saying we're multiplying that this can occur and this can occur and this can occur. So when we're multiplying, we're looking at the word and happening. So let's pop that in our calculator. And in that case, we'd only end up with just over 32 million. So we need to really look at the wording in this question and think about what's happening in each individual position when we're looking at ordered selections. Okay, so let's have a look at the next one. So it says to win a trifecta in a race. So trifecta is 3. Tri is 3. A person has to pick the horses that come first, second, and third in the race. If there are 12 horses in the race, how many trifectas are possible? Okay, so a trifecta is 3. So we would have first place and second place and third place. And there's a lot of assumptions in these questions and a lot of understanding of what's actually happening. So when we're having a horse race, a horse wins and it comes first. It can't come second or third. It can only get one place each. And that, I guess there's a lot of common sense in these questions. So if there are 12 horses in the race, there are 12 horses that could come first. First place has happened. It's crossed the line. There's only 11 horses left in the race. So there's 11 ways that we could come second. 2 horses have crossed the finishing line. There's only 10 horses racing for 3rd place. So they're the number of ways that we could get a trifecta. So let's multiply those together. So we've got 1st place and 2nd place and 3rd place. So in a 12-horse race, there are 1,320 possible ways that a trifecta could occur. So if you're betting on the Melbourne Cup and you're trying to get a trifecta in there, you've got 1 out of 1,320 as your probability as a chance of winning. So I guess you could think of it probability-wise. You've got 1 chance out of 20 of picking your first course, 1 chance out of 11 to pick your second, and 1 chance out of 10 to pick your third, which is why you'd have 1 out of 1320 to pick the possible winners. I've just jumped over to the OneNote to have a look at a couple of other questions that are nice and stock standard. It says, what number of outfit combinations can be created with 12 shirts, 6 pants, 8 shoes and 17 ties if there is no dependence or prior selection? So basically anything goes with anything. So in that case, we'll be multiplying all those together. 12 times 6 times 8 times 17. So they're the possible number of outfit arrangements that you would have in your wardrobe. What number of 5-digit numbers can be formed when the 2nd and 4th digits are more than 6? And the other digits can be any value from 1 to 9. So I think what we might do with this one is think about our little boxes that we had before. So in this case, we're not including 0. So we're going 1 to 9 are our numbers. So we've actually got 9 possibilities. So let's have a look at that. A 5-digit number. We've got 1, 2, 3, 4, 5. So we're going to think of each of those positions of that number as an individual thing happening in it. So it says here we have placed a constraint on the calculation, but there is no dependence on the later digits from those beforehand. So let's have a think again. What number of 5-digit numbers? So we've got our positions here for our 5-digit numbers can be formed when the 2nd and 4th digits, so we'll call that our 1st, our 2nd, our 3rd, our 4th, our 5th, when our 2nd and 4th digits are more than 6, and the other digits can be any value from 1 to 9. So in this case, we can allow repetition because it hasn't told us that we can't. So let's think of our first digit. Our first digit has 9 possibilities that it can take. Our 2nd digit can only be formed from numbers that are more than 6. So that can only be formed from the digits 7, 8, or 9. So there's 3 possibilities there. And we're going to multiply these together because we've got our first digit happening and our 2nd and our 3rd. Our 3rd digit, it doesn't give us any constraints, so there's 9 possibilities. Our 4th digit, we can only have digits 7, 8, or 9. And our 5th digit, we can also have 9. So that's what we're doing when we're multiplying all these numbers together. So that kind of number, we would have 6,561 possibilities. So in order to do exercise 14B, we also need to go and have a look at these things called permutations. So also something new that you have not seen before. So scroll down to that page. Permutations, there's a button on your calculator. There's a factorial way that we write it, and we need to understand what it actually means. So let's read what's up here. So factorial notation is useful for finding the number of possible outcomes when arranging all objects in order without replacement. However, sometimes only some of the outcomes are being arranged. Permutations are used to calculate these scenarios. So for example, a permutation, and P here stands for permutation. So a permutation, and we'll call that NPR. That's the name of that permutation. And I'm just going to go and grab the highlighter and highlight for us. So a permutation NPR describes the arrangement of R objects from a total of N in a certain order without replacement or repetition. So NPR is N factorial over N minus R factorial. So before we get into anything really difficult with these, let's look at the first question below. And this is looking at, calculating 8PR. So a couple of ways we want to look at that. 8PR is going to be 8 factorial on 8 minus 3 factorial, which is 8 factorial on 5 factorial. You can use a calculator if you like, or you can think of what that was. That was 8 times 7 times 6 times 5 all over 5 times 4 times 3 times 2 times 1. So you're going to get 8 times 7 times 6, which is, if we just grab our calculators and work that one out, 8 times 7 times 6 is 336. Now, let's grab a calculator up there on our screen for now, just so I can show you. There we are. So, what we also have on our calculator here is a button that we can use. So if you have a look on, I've just got the abacus up here. You've got down the bottom here above the divided by sign an NCR, but we want the one down below above the multiplication sign, so NPR. So what we were trying to work out, I'll just slide it over here. Oops, we've got a couple open. I wanted 8P3. So if I'm typing in 8, I'm going to get my yellow to get my function button up to get my P. So that's my permutation. 3, I'm going to end up with 336, which is the same as what I've got over there. So your calculator can help you, but you need to know what to input into your calculator. So that's a nice simple way to work out a simple permutation. So all our questions on permutations and then later on in combinations are going to come down to the language that's written. So we need to remember what's written in this book, this box up here. So it's saying that our permutation NPR is R objects chosen from N, but the words there are without replacement or repetition. So that will help us with question A down here. Find the number of arrangements of 4 digits that can be formed using the digits 0 to 9 if each digit can be used only once. Well, when they can be used only once, that's telling me no replacement or no repetition. So I know straight away that I'm going to be needing to have a permutation there. So I've got 10 digits. So 0 to 9 gives me 10 digits. And I want to find the arrangement of 4. So the arrangement of 4 objects that are chosen from my 10 digits without any repetition is going to be 10P4. So if I pop that in my calculator, 10P4, I'm going to get 5,040. So there's 5,040 possible arrangements of 4-digit numbers from 0 through to 9. Okay, so you could think of that question like that, but I want to think of it differently as well, because what we could think of it as, like we did above, is there's a 4-digit number. So I have my first digit, my second, my third, and my fourth. And it says in our question that each digit can only be used once. Oops. Try and fix that up. I want to highlight that so it's in our notes highlighted. Okay, so that means if we've got 10 digits, our first number could be any of those 10 digits. But if we've used one of those digits up in our first position, our second number has only 9 digits to choose from. So this is very similar to when we were doing the horse race question above. We've already used 2 of the digits up. There's only 8 left to choose from, and then 7 left to choose from our fourth position. So just for interest's sake, grab your calculator, and we've worked out our 10P4 from above, but let's just type in and see what we end up with for 10 times 9 times 8 times 7. So 10 times 9 times 8 times 7. Oh, it's the same. So it's 5,040. And if you think about what's happening there, I know I'm going into great detail, but I really want you to understand this. Our NPR said that it was n factorial on n minus r factorial. So that would be 10 factorial on 10 minus 4 factorial, which is 6 factorial. And if you think of what's happening there, that's 10 times 9 times 8 times 7 times 6, all the way down to 2 times 1, all over 6 times 5 times 4, all over 2 to 1. So what we're getting is this part cancelling with this part. So we've just got left that 10 times 9 times 8 times 7. So this is where they're all linking together, really. Okay, that's a long definition for part A, but let's have a look at part B. Okay, part B says, how many of these 4-digit numbers are even? Okay, now this is where we again have to think about what that actually means. What constitutes an even number? So let's write some even numbers down. So we've got 2, we've got 4, we've got 12, we've got 18, we've got 26. The thing that makes them even is not the first number, because in 12 and 18, that first number is odd. And in that, we've only got 1 digit. And here, our first number is even. So the thing that constitutes an even number is the last digit. Okay? So what we want to have a look at over here is to figure out what's an even number. We only want to have a look at that 4th digit. So that's the only thing that really matters when we're looking at even numbers, is that last place. So now we need to think, okay, well, how are we going to figure out, even-wise, what's going to happen there? So an even number would happen if that last digit is going to be an even number. So what even numbers do we have? We've got something that ends in 0, that ends in 2, that ends in 4, that ends in 6, and that ends in 8. So we've got 1, 2, 3, 4, 5 of our 10 digits are going to be even. So that means that of all our numbers that we've picked, 5 of the digits are even, and that relates to the last position here. So 5 out of 10 is half. So half of our numbers up here, our 5,040, are going to be even. And that's what we need to think about in that case. So I'm just going to write that down over here. So we're going to have 5,040, divided by 2, which is, 25, 20. There's 2,520 numbers that are even. So let's have a look at this last example. And this one's actually a really hard one, and you really have to think about these. So it's saying 8 people form 2 queues, each queue with 4 people. So I'm going to go, here's queue number 1. We'll call it Q1. There's 1, 2, 3, 4 people in that queue. And Q2 can have 4 people as well. So there's our queue. We've got our left hand queue. Q1 is on the left, and our right hand queue. And it says Albert will only stand in the left queue. So if Albert will only stand in the left queue, there's only 4 locations that Albert can stand. And there's 1, 2, 3, and 4. Beth will only stand in the right queue. So likewise, there's only 4 locations for Beth. 1, 2, 3, and 4. So she's only got 4 possible locations. Now, here's the hard bit to think about. Charles and Diana insist on standing in the same queue. In how many ways can this be formed? Okay, so we need to deal with these restrictions. And that's the hint. Always deal with the restrictions. Okay, so, and we've got to think, Albert's in one of these spots over here. So we might just chuck Albert over here and Beth's in there. So there's only 3 spots left here, or 3 spots left here. So Charles isn't fussed on which queue he stands in, but if he stands here, he's got 3 choices. If he stands here, there's 3. So there's 6 locations that Charles can stand. So his one's okay. Diana's the one we really have to think about. So Diana and Charles want to stand together. They want to have a chat in the queue together. So if we're over on the left here, Albert's in there, and if Charles is in there, then there's only 2 spots left for Diana. If we're over here, Beth's in here, and if Charles is in here, then there's only 2 spots left for Diana. So in that case, in either case, Diana only gets 2 locations because her restrictions are based on Charles, are restricted by what he does. Now, by now, we've probably forgot what the question wanted us to do. We want to figure out in how many ways can the queues be formed. Okay, well, we've got restrictions. So we've got Albert in 4 locations. Beth can go to 4 locations. Charles can go to 6. Diana can go to 8. But there's 8 people in this queue, and this only deals with 4 of those people. So we've got 4 more people in that queue, and there are absolutely no restrictions on those other 4 people. So once these guys, Albert, Beth, Charles, and Diana, have filled their spots in the left or right queues, our 5th person has got 4 spots left to choose from, because 4 people have taken up the spots there already. There's 4 other spots, so that next person's got 4 places to choose from. The person after that has only got 3 places. The person after that's got 2, and the last person's got 1. So if we multiply that together, that's going to give us the number of ways that the queue can be formed. And that gives us 4,608 ways. So in this case, this question's a little bit tricky because we have to think of the positions that they can take up. And we have to remember that there's actually 8 people that can go into those positions. So this first person would have been Albert, and then Beth, then Charles and Diana, and then person number 1, person number 5 actually, person number 6, person number 7, and person number 8. Okay. Have a go at the exercises and check your OneNote for some extra examples.